So I guess graphical view for expression solver will help you to understand how it works. Suppose you have matrix vector V, which is represented by matrix times solution X. And suppose you have immediate solution X. Then you can find the approximate solutions through the approximation step. If you find the approximate solutions, then you can find the residual vector, which represents by B, the difference between the vector B and A times X. So once you find out residual vector, then you can find out correction vector Z. So if you sum up the approximate solution and the correction vector, the second approximate solutions gets close to exact solutions. So this step keeps going on until you reach numerically satisfied solutions. So you may wonder how quickly this approximate solution converges to exact solutions. The answer is it depends on condition number of the matrix. So condition number of the matrix represents the stability of the matrix to solve system equations. So I guess this explanation will help you to understand that to get the concept of condition number of the matrix. Suppose you have two people, and one person is stable and one person is not stable. So when you shake unstable person, then he's gonna shout and he's gonna react very violently. Then he has large condition number. And if you shake a stable person, then he reacts silently. Then he has just small condition number. So which means that one of the elements in the matrix changes a little bit. Then solution is changed with substantial amount when the condition number matrix is large. So we have to choose precision according to the condition number matrix. So in this slide, I want to compare the mixed precision linear solver implementation in GPGPUs and FPGAs. So in GPGPUs, we can just employ single or double precisions. So normally, single precision is employed for matrix compositions, and double precision is employed for refining solutions. So if it works, then the process is done. If it does not work, then we have to employ double precision again to obtain the work of triangular matrix again, because it has large condition number of matrix. However, in FPGAs, as I mentioned before, we can employ arbitrary precisions. So we can fully exploit the precisions to optimize performance. So we can employ arbitrary precisions for approximate solutions. Also, we can arbitrary precision for refining solutions. And another benefit for the FPGA is because in refining solutions, it acts like Newton method. So actually in Newton method, then you don't have to imply highest precision for the first few iterations, because as long as the approximate solution is good enough, then you don't have to employ highest precision. So in refinement step, we can increase precision by iterations goals in FPGAs, so that we can also optimize performance for refinement step as well in FPGAs. So as I mentioned before, FPGA can employ arbitrary precision for computations. So we can select a precision based on a matrix condition number. So if you employ low precision ALU inside the FPGAs, which means you can employ the smaller and fast ALUs, so we keep the more arithmetic units inside fixed area in the FPGAs, so that you can expect high performance. So when you look at the table, when you employ single precisions, you need 2 DSP48A block to implement one multiplier, one floating point multiplier. If you employ the double precisions for the multiplier, you need 10 DSP48 blocks. So it increases quadratically about the size according to Manitiza bit width. So you can simply expect a 5 times speed up, because if you employ single precision rather than double precision, because you can keep five multipliers in the fixed area. And also, as you guess, the double precision computation takes twice than single precision computation in general. So simply you can expect around 10 times performance improvement simply by employing single precision rather than double precision inside the FPGAs. So I will talk about the power performance in this slide. So we focus on dynamic power consumptions because we are interested in the incremental performance benefit for one additional watt. So we're going to introduce, okay, this slide is about how we can drive the power performance. The total power consists of the static power consumption and dynamic power consumptions. So dynamic power consumptions can be described by capacitance load times operation voltage scale and times frequency. So we simply introduce alpha coefficients, which represents by capacitance load times voltage scale. So based on these equations, and we can simply find out maximized alpha coefficient value, which is represented by maximized dynamic power consumption divided by frequency. So we want to introduce three different performance for the power performance metric. The first one is represented by F. It just represents the flux, the number of floating operations per second. And the next one is the clock-based performance, which is represented by number of floating point operations per clock cycle. And the third one is represented by power-based performance, which is represented by the number of flops per watt. So if you look at carefully about those equations,